question on the lab that we got last week. So if it's already balanced, do we need to change anything? Okay. Okay, cool. Some of them will already be balanced, just naturally.
Yeah.
Okay. Oh, okay. That was cute. Wait a second. I like it.
Any questions before we get started? And then I do have a homeless homework up at the front. It's an older one, so chapter 3 and 4. So if it's yours, just let me know so I can put it in the grade book. So let's go over the different reaction types, just so we're all on the same page. So we'll start off with the combination reaction. And so what's a combination reaction? Anybody remember? So what's a combination? What generally is it happening?
More reactants than products.
So more reactants than products, that's a great way to distinguish. So generally A plus B gives you 1 C for your reaction. And so there's a few examples you could use. So the one that's given in your packet is reacting 2 equivalents of sodium plus your chlorine gas to give you sodium chloride. And of course it can be any combination of things adding together. And so let's look at the other type. And so there's a special class of combination reactions, and so it's down lower on your sheet. And so there's also combination combustion reactions. And those would follow that same form of two things coming together. It's just what happens when you see a combustion. What do you know is going on? What should be the reactant? Oxygen. So anytime combustion, that means oxygen has to be involved. And so it could be as simple, just like our balloon demo that we did. So the mixed balloon, remember it had that big explosive reaction since we were doing a reaction. So H2 plus O2 gave us water. So that would be a combination reaction. Of course, balance it, so 2 and 2. Or even, just simply you could combine, burn some carbon plus some oxygen to give you CO2. So this would also be a combination combustion reaction. And this one, though, forms carbon dioxide. And so while we're on combustion, so if it's not just a simple combination combustion reaction, then what are the two products of a combustion reaction? So there's always two products, and then back to the reagent of oxygen. And so what are the other two products that let you know that it's a combustion? No, oxygen's in the reactant. So having oxygen in the reactant, that's one clue that it's a combustion. But then what would the products be? Because you could also see like water. Yeah, so water. And you just want to know in case you're not told, because they could say, oh, there's a combustion reaction with hexane, do the stoichiometry, and you're not given anything else. And so what's the second product? So water and carbon dioxide. Excellent. And then the combustion, this will be generally with an organic, so some carbon, some hydrogen, and some oxygen formula. And the oxygen could be 0, so there could be no oxygens in there, but that's just the most general form. So let's look at the other types. Oh, let's talk about some other things in here. So I don't remember if your book mentions redox now, but we should at least mention it. And so let's make a new space. So if you hear this term redox reaction, all that means is you have some sort of reaction where the oxidation states change. And so kind of the key point in doing this is, so y'all have been practicing figuring out, right, our oxidation states. We know if they're in an ionic compound, we can look at the periodic table and see what the charge would be. And so that's going to be its oxidation state. And then the second half that we need to know to kind of determine if there's a change or not is, so all atoms in their elemental form have an oxidation state of 0. So that's just telling you that's your starting point. And so if we look at these combination reactions, they tend to be redox reactions. And so that makes sense. So let's look at the sodium chloride. So again, you can at least start seeing what I mean with this redox term. It'll probably crop up later, but it's good to introduce it now. So in this combination reaction, sodium's in its elemental form, right? It's just naked sodium metal by itself. And so it starts off in the oxidation state of 0. We have chlorine. Again, it's a gas, elemental form, and so it's also 0. And so now what's the oxidation state of sodium now that it's in sodium chloride? So look at your periodic table. Where's sodium? So 1 plus, and then what's chlorine or chloride? -1. And so now we can see, yes, we did have an oxidation state change. And kind of your big clue is, oh, we started something in its elemental form, and then we made something else. You'll kind of notice that trend. And so we can just say that this lost electrons to become positive, and then we see chlorine gain those electrons. But we'll revisit this probably later. And so same thing with these combustion reactions. So they would be redox reactions anytime you see combustion. So just note that. And so now let's look at single replacement reactions. Do y'all remember an example of a single replacement? You saw one in lab. It was like metals swapping.
It goes from element on one side to compound on the other.
Would sodium chloride be one?
So it has to be like reacting with something. So maybe, I was trying to think of an example. So we were saying we're swapping metals. And so just, I'll write the general form first while you think about the example. So we have some sort of compound plus something in its elemental form, and then they're going to swap partners and make new product CB, and then make A. So do you remember which one in lab was like this? You were replacing one metal with the other.
I don't remember what the one in the lab was, but there's one from the one from last week. The brown line, plus copper oxide to make iodine. No, iodine plus copper bromide.
Oh, so iodine plus, is that copper 1 or copper 2 bromide?
Copper 2.
So copper 2 bromide. And so in this case, they swap. And does that give you copper iodide, I presume?
Yeah.
And so that's one single replacement, so swapping. So then we get copper I2 plus bromine gas would be released. That's one example. So the one I was thinking of from lab is, remember when you put that piece of zinc in the copper? So you had zinc plus copper sulfate, and then they swapped places, and you formed copper metal, so it started turning orange, if you kind of remember that rusty looking thing. And so that was making copper, and then zinc sulfate. And so looking now at the redox, so single replacement reactions do tend to be redox. And so again, you're starting in your elemental form. So if we take this iodine example here, so iodine, again, elemental form, so it's going to start off in 0. Then what's my oxidation state of copper? So in this case, double check it, because we get, so copper 2, and then bromine is so -1. And then in our products, so we see we form elemental bromine again, so now that's 0. Copper is still 2+, so copper didn't change oxidation states in this case. And then iodine, what's iodine's new oxidation state? So -1. And so there you can see iodine is gaining electrons, bromine lost electrons, and copper is just hanging out in the 2+ state. And so then if we compare this metal down here, so what's zinc's oxidation state? So 0. What's copper in this one? 4. Try one more time. So sulfate, SO4, 2-, right? So +2. We'll ignore the sulfate because we can tell nothing's changing from there because it just goes from sulfate to sulfate. You could have scenarios where these change oxidation states, but I'm not examining them right now since I can tell they're the same. And then what would copper be on the product side? So 0, and then zinc. So 2+. And so there again you can see this time our zinc lost electrons and our copper gained electrons. And then the last one is going to be our double replacement. So, any examples of a double replacement, or what's the general form? How do we recognize it? So they kind of swap partners. So generally it's like A plus B plus C, and D gives you nu, AD, and CB. And so I think you had one in lab that was something of silver nitrate, and this would have been aqueous in solution, plus some sort of chloride, so it's probably sodium chloride in lab. So again, that would be aqueous, so 2 solutions, and then we mix them, so then that would give you silver chloride. And so kind of the key thing too with the double replacement reaction is they are driven forward by either precipitation. So anytime you see, right, when you would mix things together in last week's lab and you saw something cloudy forming, that's telling you that you're forming a precipitate, and all that means is some sort of solid is coming out of solution. And so silver chloride is pretty insoluble, and so it starts to come out of solution, and it has to come out of solution to keep driving that reaction forward. And then our other product, so sodium nitrate. And so I think we might touch on this more later, but again, just giving you a preview of what drives this forward. And so the other thing that drives this forward is also water formation. So if you form water in some sort of neutralization, that can also drive your reaction forward. Trying to silver. And so some example, and again, this is we'll say a glimpse into the future. Of course, I can't spell. Looking at the future. And so why I'm emphasizing this precipitate is, let's say you had this reaction, so sodium acetate plus silver nitrate. And so in theory, we would do the same thing, swap the partners. So Ag, or silver acetate, plus sodium nitrate. And so this looks like it would react. You would think you might expect something. But again, looking into the future, we'll later find out that this is actually soluble, meaning that there's nothing driving forward the reaction. And so they would just be staring at each other all in a beaker. And so what that would really look like is we have our beaker of solution, so we just have sodium ions floating around, acetate ions floating around, silver ions floating around, and nitrate ions floating around. And they'd be floating around, they could meet with one another, but then if there's no insolubility to, again, drive it out to precipitate, then they're just going to meet and float away again and just be floating around. And in that case, you could just put like AQ, AQ, and no reaction. But again, we'll hit this up, I think, later in the course when we talk more about solubility and solubility rules, but that kind of at least tells you where we're going with that. And then, so the other thing about double replacement is they are not redox reactions. At least for the most part, so not redox. So if you're just swapping cations and anions, so if we just examine this first one, silver's in the 1+ state, sodium's 1+, chlorine's -1, then silver's still 1+, chlorine's still -1. So nothing happened, right? They just swap partners, so not a redox reaction. And then just the last one on your chart, and this is kind of the special scenario. So double replacement / decomposition. And so those tend to occur. So let's look at your example. So you had hydrobromic acid plus calcium carbonate. And so let's first figure out, well, how do they get the decomposition? And so you could treat it like a double replacement reaction, because that's what you would expect it to do. So then you make calcium bromide, and then carbonic acid, so H2CO3. But then the problem with this is it decomposes right away, and so this gives you carbon dioxide and water. And so that's why in your lab it just gives you the final shebang, so 2 HBr plus calcium carbonate gives you calcium bromide plus CO2 plus water. And so it's generally with the carbonic acid product that you see this, so this is not stable. And you might be aware that there's some sort of equilibrium, you know, with carbon dioxide and water. So it is slightly soluble, and it does form a little bit of carbonic acid. And again, they're just in equilibrium. And then last but not least, so we don't forget it, is the decomposition. And so how do we recognize a decomposition reaction?
Splits from one compound into two elements.
So it goes from 1 to 2, or maybe even more. And so they gave a very simple example of just sodium chloride. So you could split it back up to give you sodium and chlorine. Other decompositions, so if you could use, so they're trying to use water as a fuel, and so water splitting, you can split that, of course, into H2O and O2. And so what do we think? Do you think decomposition reactions, will they be redox or non-redox? So I saw a nod for redox. So yes, we do expect them to be redox. And so in this case, right, you're starting with sodium in the +1 form, chlorine's -1, and then we make their two elemental forms, so they would go to 0. So we could see we had an exchange. Right. Does that make sense on the types of reactions? So now let's shift gears and go over, we'll do some of the homework practice and some of the lab. So let's start with lab, actually. These could be tricky. So let's start with the pre-lab, and we can do this kind of together. And so let's look at number 1 here. And so number 1 is just practicing writing these decahydrate formulas. And they give you kind of this example here. So we see for cobalt 2 chloride dihydrate. So there's our di telling us how many waters. And so this is how we write it. Remember, we have that little dot here just to say we have 2 molecules of water complex to this cobalt chloride. And so what would we write for sodium carbonate decahydrate? What's the formula?
Na2 and then CO3 times 10H2.
So just like that. So that looks good. So that's the first step. And now it's trying to walk you through the process. So just like you'll be doing in lab, so you'll have some hydrated salt, you'll heat it up and make the anhydrous version. So now we want to write the equation. And so this is our starting material. And so this is technically a decomposition reaction. And so we'll heat it and it'll decompose and make 1 equivalent of sodium carbonate plus our 10 equivalents of H2O, which would probably be in the gas form as it gets heated and flies away. And so now let's look at part 3. And so part 3, it's really a stoichiometry problem, so we can take everything that we learned on Monday and apply it now to this class, or this problem, I mean. And so we start with a 3.25 gram sample of an unknown hydrate of calcium chloride is heated. Okay, so let's start with that. So we know we have calcium chloride. I don't know what X is yet, but I have X amount of water. And so it's heated to remove the waters of hydration. And so that means that we're going to form calcium chloride plus X amount of water molecules. And let's just write, so we started with 3.25 grams of this. And then it says the mass of the sample after heating is 2.54 grams. And so now it asks what's the formula of the hydrate. And so this is exactly what we're going to be doing in the lab. And so what we want to do is we need to find the moles of our calcium chloride product, so we have mass of that. We can find molecular weight, right? We know how to do that. So we can find moles of calcium chloride. But then how do I find moles of H2O? What do I need to do? So subtract these two, right? So because right, our mass lost, so the difference here should correspond to the H2O lost. So you'll do this in lab. So you start with 3.25 minus 2.45. Oops. And so that just gives us 0.8 of H2O. And so now we're set up to do everything. So let's find moles of calcium chloride. And so we need the molecular weight of calcium chloride. So take a minute or so. Let me know what the weight is. Do you have a mass there? Homeworks. And then this is the lab, so if you want copies of the lab, I can go to lab and grab them. I think I have. All right, who needs homework? I'm doing mine now. Do you want copies of the lab too? Okay, let me go. I'm gonna grab the lab. Okay.
Oh, yeah.
So lab, who's in the lab? Lab? Anybody else in the lab? So do we tally up our mass of calcium chloride? 110.984. Is that what other people got? Sweet. So now we have, so that's our grams per mole. So we can find moles of calcium chloride. So 2.45 grams, now divided by our molecular weight. And so how many moles do we get?
0.022.
.022. Is that what other people got? So 0.0242 or 43 or something moles. So now we have moles of calcium chloride. That's good because, right, we're just trying to find the ratio between them in whole numbers so we can get the formula. And so now let's repeat that for water. So find moles of H2O. So we have 0.8 grams. And then, do y'all remember the mass of water? 18 grams per mole. And so how many moles of H2O does that leave us? I think something. Did you do 0.8 divided by 18? So I see none. So do we get this 0.04444? So 0.0444 moles. And so now we have how many moles of each, but this doesn't give us a formula yet. And so the last little step is divide by the smallest amount of moles so we can get some sort of whole ratio. And so in this case, right, this is our smaller one. And so we'll divide, so of course calcium chloride divided by itself just gives us 1 back out. And then if we take our 0.04444 divided by this number, what do we get? So 1 point, what did you say? 8289. And so that's really close to 2, right? So we want whole numbers, so we can probably just go ahead and round this to 2 pretty safely. So the only time I wouldn't do rounding with this scenario, if you had gotten like 1.5, you'd want to double it. 1.3, like I don't like rounding 0.3, that can be a little off, so you might want to multiply that by 3 to get your whole number ratio. But in this case, it's good enough to assume. And so then we can write our formula of calcium chloride, and then we know there's 2 equivalents of water, so calcium chloride dihydrate. So now let's look at the post-lab questions. And so this problem always gives students some issues. And so see if you can read it, and I'll give you all a few minutes to start it, and then we'll go over it. And so it starts off with, so a student heats up 4.75 grams of copper 2 sulfate pentahydrate. So we know what we're starting with. And then, of course, in order to drive off the waters of hydration, at the end of the experiment, the mass of the anhydrous copper 2 sulfate is determined to be 2.82 grams. So it says write a balance equation and calculate that theoretical yield. And then percent yield. So think about what we did on Monday. Try to set this up like your regular equation, like a stoichiometry thing. You're given how much you have of your starting material. So hint, hint, try to use this to figure out, well, how much copper sulfate would I get then? Anhydrous, if it is completely 100% completion, you know, you're there in lab heating up that crucible of copper sulfate, how much should you expect to weigh? So take a few minutes, see if you can solve that. And so I see a lot of blank pages right now. But just start with the balanced equation, right? So what are they saying? So write out your little recipe. So we have copper sulfate, pentahydrate, so 5, decomposing, so copper sulfate, plus 5 equivalents of H2O. And so now you're looking at this, right? It's balanced. And so kind of the key here is they're in a 1-to-1 ratio. And so see if that hint helps you. And so you probably want to try to figure out moles of copper sulfate pentahydrate first, since you're given that, right? Because we're trying to use this information to figure out what's my 100% yield of copper sulfate. Because this is just your actual yield, so it really doesn't have, meaning here other than it's what we're going to be calculating our percent yield from. Did everyone get back midterms? So what should we be calculating first right now, or at least probably have to find a molecular weight of something, so what do we need to do?
How much are the elements weigh?
So find, I'd say let's find the molecular weight of copper sulfate. And really you want both of them eventually. So copper sulfate and the copper sulfate 5H2O. So does anyone have the molecular weight of copper, either copper sulfate or the copper sulfate pentahydrate?
Copper sulfate was 159.612.
Sorry, I didn't hear. 159.612. Is that what other people got? Relatively close. And then what do we get for the pentahydrate? So we just have to add plus 5 times 18 to this. So what do we get for this mass? 249.612. So is that what everybody got? That sounds about right. 5 times 20 gives you roughly 100. So now we have our 2 molecular weights. And so now the next question is we can find our moles, do our mole-mole ratio, and get our theoretical yield. So let's do that. So 4.75 grams of the copper, I'm just abbreviating, of the copper 2 sulfate. So now this is just like our good old stoichiometry. So divide by our molecular weight of the pentahydrate. So that gives us 1 mole. And then formally, so we could do, right, a mole-mole ratio, even though it's pretty obvious in this one, but we could still write it. So 1 mole of copper sulfate anhydrous can be derived from 1 mole of our pentahydrate. So that just gives us times 1. And then the last bit is then, of course, going back from moles to gram. So moles, now we need to go to grams. So now we'll just multiply it by the mass of our anhydrous. And so now if we plug all that in, what does that give us? So I get like 3.03. Thumbs up, thumbs down.
But would it round up to 3.04 though? Does it say?
Oh, yeah, so we can round it up to 3.04 then for sig figs. So 3.04 grams. And of course, you could have something slightly different with rounding, depending on your numbers here. But something like that. And then our last step, so what do we have to do at the very end? So how do we get our percent yield? So this is our theoretical yield now. So again, that's just saying if we were perfect and everything was perfect in a perfect world and we could get 100% recovery, this would be how much we would expect. And so what do I need to do to find the percent yield? So actual over theoretical times 100, and so we have the actual one there, and I'm running out of space, but 2.82 divided by your answer. And should be a fairly high percentage. 92.7%. 92.7, that sounds good. So does that make sense how to approach this problem? So don't let it freak you out. You know, just do your mole ratios, do your stoichiometry. And then what you could do too, again, as you practice, you might see different little tricks. And so the other way to do this, let me just start a new page. So alternative method. So you could also set up a proportion, which if that's easier for you, you know, go ahead and do it. So they're in a 1-to-1 ratio. So copper sulfate to copper sulfate pentahydrate. And so then you could say, you could set up a proportion with their masses. And so now I forgot the masses. So we had 159.612 for the regular copper. And then, what was it, 249? 0.12, 612. And then, so then we could set it up so copper sulfate's on top. So this would be X, because that's what we're trying to find. And then we can put our weight of our starting material. So that was at 4.75. And so this is the same thing that we do with the stoichiometry. And so just to prove, so 159.612 times 475, then divided by 259.612. And so that also gives you the same answer. So again, whatever way is easier, I just encourage the stoichiometry way since that follows dimensional analysis, but you can always do a proportion.
How does it get multiplied by the 4.75?
Oh, so you do, so to solve it, you do cross multiplication. So it's 159 times 4.75 divided by the 249 to solve for X. And again, it's just whatever you feel comfortable with. So practice, whatever makes sense to you, whatever really clicks in your brain. So now let's look at the homework. I think that's all I wanted to cover from the lab. And so let's look at these since we didn't quite talk about this explicitly, we just kind of mentioned it. And so let's look at number 2. So it says calculate the number of O2 molecules in 100 grams of O2 gas. And so see if you can figure out how to approach it. And don't forget about that Avogadro's number. So 6.022 times 10 to the 23rd is 1 mole. And if you didn't get a mole highway, I have a few copies here, and I can always make more. missing from this. Oh, there's too many pages. Plenty more copies.
Oh, and then. Guys, you have extra molds, I don't know why I have more of these, so, here you go. Can I have one of those? I think they're awesome. Thank you.
Always make more copies. Yeah. So if you're not sure what to do, then you can always look at this mole highway to kind of help you. And so we go back to our problem. We have grams. We're trying to get to molecules. So grams, want to get to here. So it looks like we need to go grams to moles to particles. So then we can think about setting that up. So we can start with 100 grams of O2. And then what's the molecular weight of O2?
31.998.
So 31.998, and you could definitely round that to 32. And so now we're at moles of O2. We need to go to molecules. And so that means we need to multiply by Avogadro's number. So again, there's our conversion factor. So moles would go on bottom to cancel out. 6.022 times 10 to the 23rd on top. And so what do we get for number of molecules?
I got 1.882 times 10 to the 24th.
1.882 times 10 to the 24th. That sounds good. Is that what other people got? Awesome. You probably want to keep, yes, in this case, 4 sig figs. And then you can ignore these all in the conversion factors. So let's look at 7. So see if you can figure this out. So calculate the mass of 100 trillion water molecules. So that's 1 times 10 to the 14th. And could we see a sample of water this small? So start walking me through this. We start with 1 times 10 to the 14 molecules, and then what do I need to do from here? So what's the molecular weight of water?
18.015.
But then I can't just go from molecules to this yet, right? I need some factors. So just looking at my units, I have grams, I have moles, but then I have molecules.
So you guys have to like multiply or divide it by the Avogadro's number.
So excellent. So divide by Avogadro's first. So 1 mole, 6.022 times 10 to the 23rd molecules or things. And so now that gives us moles. So now we can multiply by our molecular weight. So 18.015 grams over 1 mole. And so what do we get when we plug this in? So I've punched something like that in. So is that what other people got?
For this, what would the significance be? Because I always like the 100 trillionths. Would it just be 1? Remember, I was so free.
Yeah. So they didn't give us too much to work with, so I guess we have to round it. Yeah, 3 times 10 to the negative 9 grams. And so do we think we could see a sample this small? Yeah, probably not. So generally, like your limit on balances is going to be about 1 mg is the tiniest you could measure out and see on a balance. And then beyond that, if you were making like really dilute solutions, that's where you have to do like serial dilutions generally and make it dilute. Let's see what. Let's see. Which one of these is trickier? Any requests, or should we just try this one? We could also.
Have the A,
Which one?
the A on that first page. Yeah. Or you have to start with the first.
Yeah. So let's look at A. So see if you can balance the equation real quick. And then we can start doing A. So do we figure out our coefficients for balancing? 4, 3, 2. That looks really good. And so now I'll let y'all move on to part A. So we have our balanced equation, good. Now, how would we figure out A?
You have to put the ratio for it. Is it kilograms?
Yeah, so we'll have to go grams to moles of aluminum, and then we have our mole ratio here, so 4:3. I'll give everyone some more time though.
Is the molar mass the same thing as the molecular weight?
Yeah,
Okay.
and sometimes it's called formula mass too, like you might see like FM or FW for abbreviations, it's all the same thing, molecular weight. So let's start working through this. So tell me what you did. So I'll start with my 2.75 grams of aluminum. And so now what do I need to do?
The molar mass?
So molar mass, and so what's the molar mass of aluminum? 26.982. So now let's divide to get moles. And so now we're at moles of aluminum. And so where do I need to go next? So give my ratio, so they're 4:3. So which number goes on top? Which number goes on bottom?
4 on top, right?
So not the smallest, but remember, if this is giving you, so you have to think about your unit. So this is giving you moles of aluminum. You're trying to go from moles of aluminum to now moles of oxygen with this step. Exactly. So it has to cancel. And so that means that aluminum has to go on bottom. So that's 4 moles of aluminum to our 3 moles of oxygen. And so, yep, now they cancel. Okay, my unit is moles of oxygen, except they weren't asking for moles, they were asking for mass. And so what's the last little step? And so what did we say that was? We just calculated it. Oh, remember it's oxygen though. Yeah, so O2. So anytime you see like oxygen in a word problem, you know it's diatomic.
It's 31.998.
31.998. And so now we can go ahead and multiply that. So that's grams per mole. And so again, that means our moles is canceling out. And now we just have to plug it all in. And somebody can shout an answer at me. So I got this answer. Thumbs up, thumbs down. Yeah, so nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. So have those highlighted, circled, whatever on your periodic table. I would probably highlight them with a highlighter. If anyone needs a highlighter, I have one. And yeah, just anytime you see those in the word problem, you want a highlighter. Yeah.
Nitrogen, oxygen, fluorine, bromine.
Let me see if I can find my periodic table. So yeah, hydrogen. So remember your 7 diatomics. So hydrogen is the lone one. And then nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So just highlight those or whatever, circle them. So just, that's the tricky part. In the word problem, you see that, oh, okay, I gotta know it's diatomic. Oh, I lost my page. And so were we all good with this answer of 2.44? So I see some nods, other nods, excellent. And so we need 3 sig figs, so 2.46. And so let's do B, so then we can do C. And so take a minute or two. We're starting to run out of class time. Take a minute or two. What's the formula to of aluminum oxide? Get that molecular weight.
With oxygen, we got like 2 with, is it aluminum oxide or only if it's oxygen?
It's only if it's oxygen. And then aluminum oxide, that's where you have to go back. And so you were given the aluminum oxide here, but let's say you weren't, right? Then you can just start off, okay, I know there's aluminum. I know there's oxygen. Aluminum's always 3+, because that's one of those that's always 3+. Oxygen's -2. And then by the swap trick, you get that Al2O3. So that's how they got that formula. So I think I've stated this before. It's like the final is not technically over the first few chapters, but chemistry is just cumulative by nature. So just for the sake of time, I'm gonna go through this. So 2.75 grams of aluminum. So we can start off with the same process we did up here, right? So same thing, just finding moles of aluminum. And so now we have to do our mole ratio of aluminum to aluminum oxide. So that's a 4:2. And so now my 4 will go on bottom, 2 equivalents of aluminum oxide on top. And then does anyone have the mass of aluminum oxide handy?
101.961.
So 101.961. And so then we can multiply that at the end. Did I type something in wrong? Oh, that might be right. I might just be. I think I was just tripping for a second. All right, so 5.2 roughly. Yeah, I was being crazy. And so the last little part, and I know we're almost out of time, so it's saying is it consistent with our law of massive conservation? And so to see, we have to take our mass of aluminum, so 2.75, plus our mass of oxygen that we said would react, and it is consistent. So we are expecting about 5.21 by mass balancing, and that is indeed what we got. And so I'd say yes, they are consistent. All right, I think we'll have to end there for the sake of time, and then I will see half of y'all in lab in 10 minutes. And then make sure that's not your homeless paper. I have homework. If anyone still needs it, one mole highway for one lucky person. Then I will gladly accept papers. Again, hopefully everyone got a midterm back. They should have. If not, I ate a bunch of papers somewhere.